Part 2, piecewise functions and their limits. Alright guys, so some functions are not described by a single equation, but a whole bunch or multiple equations. These are called piecewise functions because there are functions in pieces. Make sense? The graphs of these pieces can join up and be continuous, okay, at their boundaries, or not join up and be discontinuous. It just depends on what the graph is. Okay, you've never done things like this, so bear with me. We'll muddle through it. Okay, so the first example. So consider this function. So it's a piecewise function. So the function is defined as x squared for all values that are less than or equal to 1. Okay, and the function is 3 minus x for any values where x is bigger than 1. Okay, so here's what we can do, or how we can do this. Okay, I always like to draw the boundary line. So the boundary line is x equals 1. Okay, so that's this line here. It's not so much an asymptote. It's just where the piecewise function breaks. Okay? Alright, so the thing is, so for less than or equal to 1, so that's like this side of the graph, the function is x squared. Well, what does x squared look like? Okay, well, x squared is a parabola with a vertex at 0, 0. Now, if you don't know this, it is quite helpful to evaluate this function at the boundary. So basically it'd be f of 1 of x squared. Okay, so that of course is going to be 1 squared, which is just 1. Okay, so, and that's good because we know that a parabola does that. Okay, so it's looks like, oh, sorry, that's not what I wanted. There we go. Alright, so a parabola looks like this, more or less. Okay, the important part is the boundary, and at the boundary we are allowed to equal 1. So we have a closed dot on the 1. Okay, so now let's evaluate the other function, 3 minus x. So f of 1 of the other half. Okay, so 3 minus x, that's going to be 3 minus 1, which is 2. Okay, so that's going to be 1, 2, and because it is just greater than 1, there's an open circle at 2. Okay, so open circle at 2. Okay, and now it's the graph of 3 minus x. So really, guys, that's just negative x plus 3. So we have a y-intercept at 3, so 1, 2, 3. Okay, I'm going to draw this part in red because this is a little bit confusing. Okay, so to draw this, okay, so 1, 2, 3. So that's where the y-intercept would be. And we don't actually start drawing that graph until we hit x equals 1. Okay, so x equals 1's there. Okay, and we having a negative slope of 1 over 1. That's 1 down, 1 right. 1 down, 1 right. 1 down, 1 right. 1 down, 1 right. Okay, so all those dots. And we only start drawing this graph at the boundary of x equals 1. So it looks like that. So that's your very first piecewise function. Okay, so that's kind of neat. So we draw the whole graph, okay, and then we have a look at what they're asking. All right, so the limit as x approaches 1 from the left, okay, well, that was just 1. The limit as x approaches 1 from the right. Now remember, even though we're not allowed to equal 1, it still is getting closer and closer to a certain value. Well, that was this part. Okay, so that equals 2. Okay, so basically the function evaluated at 1 for each half, right? That one was there. This one was here. Okay, look how they're not the same. Okay, so then we say that the limit as x approaches 1 is undefined. Okay, number 2. Show that the limit as x approaches 0 of absolute x equals 0. Okay, well, guys, we know what absolute x looks like. It's the v graph. Looks like that. But really, the absolute value is a piecewise function. Okay, so we're going to redefine that as absolute x equals. Okay, well, absolute x is just positive x if x is bigger than or equal to 0. Sure, I'll change pen color again. Okay, so it's positive x. So here, that's the positive x part. If x is bigger than 0. And of course, the absolute value is negative x. Right, slope of negative 1 when x is less than or equal to 0. Okay, that's interesting. So, the limit of this function as x approaches 0 from, okay, yep, 0 positive, so 0 from the right. Okay, well, that's 0. The limit as x approaches 0 from the left. Okay, well, that's also 0. Okay, therefore, the limit as x approaches 0 of absolute x is 0. And that kind of makes sense. It looks like it's a point, it's continuous on the graph. Okay, so left hand, right hand limits, and we just have absolute value as these two parts. Moving on. Okay, so example 3, we're going to talk, this is called the Heaviside function. Okay, and it is a function for electrical current as a function of time, and it's defined as h of t is 0 if t is less than 0, or 1 if t is bigger than or equal to 0. Okay, so if h of t is 0, remember h of t is just y, so y is 0 if t is less than 0. So that's this line here. Okay, it's that sign there, so that is an open circle, right? We can't equal 0 on that part. Okay, and then y equals 1 when t is bigger than or equal to 0. So 1's there, so closed circle for that, and then just a sideways line this way. Okay? All right, so when x approaches 0 from the left, my limit is 0. When x approaches 0 from the right, my limit is 1. Okay, and we notice there that the right hand and left hand limit don't equal. And on the graph, it's very clear that there's a discontinuity here. So we say that this is undefined. Okay. Ooh, a triple. Okay, now this one is a little bit weird, guys, so just bear with me, but it's all right. The first thing I like to do is let's evaluate these limits at the boundary points. Okay, so negative x minus 2, let's look at that at negative 1. All right, so negative 1 is positive 1, minus 2 is negative 1. Okay, so that equals negative 1. Okay, then x at negative 1, is negative 1. Equals negative 1. Or, okay, at positive 1, it equals just positive 1. Wow, it's a groundbreaking. Okay, at x is bigger than or equal to 1, so then we got x squared, so 1 squared minus 2 times 1, so that equals negative 1. Okay, so we know that the boundaries are 1 and negative 1, so let's just put those on really quick. All right, so the first part, and we are less than or equal to negative 1, so we're going to have a closed circle at negative 1. So when x is negative 1, y is negative 1 with a closed circle. Okay, now we're going to graph this part. So negative x minus 2. So that has a y-intercept of negative 2, and it's a negative slope. So one back, one up. And so it's going to look kind of like that. Now remember, it only exists, that part of the function only exists when we start at negative 1 or back. So we go to our graph, negative 1 or back, and then we, apply our slope. So back, something like that. Awesome. Okay, so now we're on the middle graph. So y equals x. Okay, remember y equals x is a straight line, diagonal line that goes like this. Well, remember, the boundary is between negative 1 and positive 1. Okay, so we go from there to there. Okay, that's the only part of the graph I draw. Alright, so over to our real graph. So negative 1 up to positive 1. Okay, now we don't put any circles on that particular graph because we can't equal negative 1 or 1 on this part. But oh look, there was already a closed circle here, right, from the other part of the graph. So we're continuous at negative 1. Well, that's cool. Alright, now the next one, that's a little more tricky. So x squared minus 2x. Minus 2x. Okay, you can graph this on your graphing calculator and get kind of an idea of how it works. We already know that it equals negative 1 at the boundary line. So the boundary line is here, this dotted line, right? That dotted line right there. Okay, and it equals negative 1. Okay, and it is a closed circle there. Okay, so now that we know that it's a closed circle, it's not going to line up with the other one. Now I can put an open circle there. Right, and that's an open circle because of this. But I didn't want to put an open circle just to fill it in. So, anyways, now that we know there's a discontinuity there, okay, we just keep going. Now, remember this graph, okay, we can graph this in a number of ways, but the easiest, so let's find the zeros, so x minus 2. So the zeros for this function are at 0 and positive 2. Okay, and we already know that there's a point 1, negative 1. We knew that from up here, right? We solved for this part of the equation. We put in x is 1, and we got y is negative 1. So the function, this looks like this. Okay, it's a parabola. Okay, now remember, our dotted line is here, so we really only have this part of it. Okay, so then we go back over to our graph, and that looks like this. Okay, so there's our picture. Wow, hey, that was intense. Okay, feel free to rewind this and have a look at that again. But anyways, now that we have our picture, now it's easy, because I want to determine whether the limit at negative 1 exists. Okay, so the limit as x approaches negative 1, negative 1, okay, from the left, okay, well that equals negative 1. The limit as x approaches negative 1 from the right is also negative 1. So the limit as x approaches negative 1 equals negative 1. Awesome. And we can see that right from the graph. That's what the y is approaching. Now you can also see from the graph that the limit as x approaches positive 1 isn't going to exist, right? Is the one side approaches positive 1, the other side approaches negative 1, so the limit as x approaches positive 1 is undefined. Awesome. Well, thanks, guys. Again, the concepts are starting to get tricky. I understand this piecewise function bit, that these are challenging. Not impossible, but they're challenging. So if you need any help, give me a call. Thanks.